Hi, everybody. This is Matthias Friedrich today from Montreal, and welcome you to today's CMR Journal Club. And I want to already thank Felicia Seemann as one of the first authors of the papers we discussed today, and a few others. And today's topic is actually pretty interesting. Pressure volume loops, at least in my training, was always considered one of the real big biomarkers we can have to assess cardiovascular function. And MR has often been asked to eventually go to one of the holy grails, and while I was never a fan of that, for example, coronary angiography was considered for a while the holy grail for CMR, which is definitely not true. But then if there is one marker that deserves some of that kudos, it's probably pressure volume loops, and that's why it's very important to have that marker. And of course, imaging itself cannot measure pressure directly, but there may be actually ways now to do that, at least with some tricks. So that's why I think today's Journal Club is very interesting. It's about quantifying these pressure volume loops in the left ventricle from CMR images and some other data. And we will discuss two papers. And without further ado, I wanted to ask Negar Musavi from our team here in Montreal to maybe share the screen and walk us through the papers, and then we'll have some time to discuss that. Negar, take over.
Hello, Matthias. I'm just going to share my screen.
Yeah, there's sometimes there are two windows in Zoom, and one of them and at the bottom has like a little menu bar, and there's in the center there's a green button with share.
Yeah, I don't see.
Yeah, so you have to identify both windows, and one of the Zoom windows will have that.
I apologize, I can't find that.
Or can you go to the top of your menu bar and then go, there's Zoom and then meeting, and then if you go in meeting, it says start share.
Yes, perfect. Okay.
Okay, so that's the other option.
Okay, so sure, perfect. Fantastic. Okay, sorry about that. Hello.
No,
so there are two papers that I'm going to be talking about. One is let me just share the screen there. Okay, so on the evaluation of elevated end diastolic pressures in patients with preserved EF, heart failure with preserved EF or HFpEF using basically CMR published in European Radiology. So just to give a little bit of background, patients, so in heart failure, we have two types of patients with reduced EF and preserved EF. And preserved EF heart failure patients, it's sort of the same amount of burden as the reduced EF patients. The problem with this group of patients is the challenge is sort of diagnosing these patients because they have normal ejection fraction. In these patients, the end diastolic pressures in the ventricle is elevated. And the gold standard is basically doing invasive angiography to assess the pressures in the left ventricle, and it's invasive. Echocardiography can also give you assessments of an estimate sort of your end diastolic pressures. With MRI, also in addition of assessments of systolic function, using the time volume curves and strain analysis, we could quantify a diastolic function as well. So that was the aim of this study, to sort of validate some CMR parameters, a diastolic parameter and then a strain for estimation of the left ventricular end diastolic pressure in HFpEF patient, and compare them with the cardiographic parameters as well. So was 60 patients with heart failure class 2 to 3 symptoms, and that they all underwent echo, basically CMR, and left heart catheterization within the 2 weeks of each other. The EF cutoff was 50%, so anybody above 50% was kept in the study. And so everybody underwent all these 3 tests, and if the end-diastolic pressures measured by CAT was above 16, this group of patients were heart failure HFpEF. And if not, they basically were not heart failure with preserved EF patients. Overall, at the end, from the 60 patients, they were able to analyze the total of 51 patients. So patients underwent echocardiography, and the usual diastolic parameters were assessed, including E, A waves, E prime, E to E prime. This is usual standard diastolic assessment. In terms of the CMR parameters, it was the study was done, I believe, on a 3 Tesla Philips machine. And in addition to systolic parameters, the time volume curves were also generated. So I'll actually show you the time volume curve that was generated here. And using this time volume curve, the different parameters, including the peak filling rate, was obtained. Basically, it's defined as the maximal change in the LV volume during sequential temporal phase. It's basically the steepest gradient in the curve in early diastole. In addition to the PFR, the time to PFR also, which is from systole to this time, and also indexing the PFR to the end-diastolic volume and percentage the PFR over 1 heartbeat. So these were a few of the diastolic parameters. PFR, time to PFR, percentage to PFR were also assessed. So let me go back to the method section again. And also everybody, so echo, CMR, and in addition to these diastolic parameters, strain was also assessed. The myocardial deformation, radial strain, circumferential strain rate, and longitudinal strain rate. And everybody obviously underwent a left heart CAT. So let's look at the results. The baseline characteristic is in table 1 that you can see here. 26 patients non-HFpEF and 25 patients HFpEF patients, and pretty similar baseline characteristics basically. So in terms of the echocardiography, diastolic parameters and CMR parameters, we look at the results in figure 1 and table 2. So I'm going to minimize the paper so you could see figure 1. This is the echocardiographic parameters and comparison between the 2 groups, E to A, E prime, and your E to E prime ratio. Basically, what was mainly significant, it's important, is your E to E prime that was higher in patients with HFpEF, and the E prime that was lower in patients with HFpEF. That's basically what we know. When we go to table 2 and 3, these are the results of the CMR parameters. In table 2, you can see, again, non-HFpEF patients comparison with the HFpEF patients. The PFR, and which is indexed to EDV, was lower in the HFpEF group, significantly lower. The time to PFR was higher, and the percentage time to PFR was higher. And in addition to that, the LA volumes were also higher in this group. So those are the CMR, just diastolic parameters. And when they looked at the strain parameters, the longitudinal, circumferential, radial, all were basically significantly different in the heart failure HFpEF group, and they were abnormal and reduced. Then what they did was look at the correlation of the EDP that they had obtained from the CAT with these parameters, with the echo parameters and the CMR parameters. So here you have your R and the P value, and you can see basically what's more, the strongest correlation is your E to E prime by echo, and your strain rate, your longitudinal strain rate. And there's also good correlation in TP, the time to PFR, and also percentage time to PFR with an R of 0.28 and 0.38. They did also look at the cutoff of EDP of 16. So if they had a cutoff, let me find that graph, where they used the cutoff of 16. it's lower down here, and association of sort of its ROC curves, E to E prime, percentage of time to PFR, and longitudinal strain, again, very good correlation, and that using that cutoff. And the sensitivity and specificity that they got was around here. It's for E to E prime is about 70% and 90% specificity, very similar with the longitudinal strain rate, the sensitivity specificity, which is interesting. So echo E to E prime is a good predictor, also the longitudinal strain rate as well. So overall, basically, to summarize, these CMR parameters added information in terms of diastolic assessment of the patient, and perhaps these parameters should be used in algorithms in assessment of diastology, and specifically in these patients with heart failure with preserved EF. So that was a summary of this paper. I could move on to the next paper, Matthias.
Yeah, maybe, but I would like to open the discussion. If anybody has a question or so, just unmute yourself and speak up, or type the question into the chat. Then I can see it here, and then I can ask the question for you. It's just from a high-level point of view, Nigar, you're also doing a lot of echo. So of course, some of the concerns would be, first of all, that the scatter of some of the data points seem pretty significant. And then the other maybe major concern to be mentioned or discussed would be, is the temporal resolution really good enough? We know in echo we have a much higher temporal resolution, and the number of data points we can get to, for example, look at strain rates is much higher. So what do you think, as someone who does both MR and echo, do you feel comfortable with the temporal resolution of MR to calculate parameters like strain rate and change of volume?
Yeah, that's a great question. I think it's very reasonable. The problem with echo, we use it with very high temporal resolution, but we have a lot of limitations on the other hand with echocardiography. The main limitation of echocardiography would be the window. And being able to properly, you need a proper E prime and proper diastologic parameters. So if you don't have the window and you don't have that, you're going to be missing your to E prime. And there's also it's E to E prime in echocardiography. It's load dependent as well. So and again, the windowing is a major limitation that we don't have in CMR. So I think taking everything into account, it's a great addition. Using these parameters would have with MRI.
Okay, so bottom line would be echo has also its limitations, and I can actually confirm that also it depends a lot on the experience of the sonographer. Is the ultrasound being really directed well enough that I can get a good assessment of the flow? So you're right, there are certainly limitations that affect echo as well. Okay, thanks. So if there are no other questions, then Nigar, why don't you go ahead and then move on to Felicia's paper?
Okay, perfect. So this is very nice paper on the non-invasive quantification of pressure volume loops using the brachial pressure and cardiovascular MRI. Just for people who might not be familiar with the pressure volume loops, it's very nice graphs, by the way. So this is basically the pressure volume loops that it gives you an idea of the cardiac mechanics. So by echocardiography, you usually get an ejection fraction measurement, so which might not be enough. So with getting a pressure volume loops, we have basically what you're looking at is diastasis. You have your isovolemic contraction time, your ejection time, isovolemic relaxation time. This is what you have. Basically, you're getting your stroke volume, cardiac input, cardiac output information here. You also have assessment of what you're looking at, ESPVR, EDPVR. ESPVR is basically your maximal pressure that can be developed by the ventricle at any given LV volume, that actually represents the end-systolic elastance. It provides an index of myocardial contractility. ED-PVR and diastolic pressure volume relationship, it describes the passive filling of the ventricle, and it indicates indicative of ventricular compliance. So a lot of information we are getting. The area under the curve, it's basically your stroke work. And that means the external work performed by the myocardium to eject blood. And here, the potential energy on the left-hand side here is basically the internal energy that the heart overcomes to eject blood. So overall, this area, you're looking at an estimate or an approximation of the myocardial oxygen consumption. So it's a lot of information that it provides, the PV loop, pressure volume over loop. The problem with it is that you need invasive assessment of your volume and your pressure to have the loop. So the aim of this study was basically to see if non-invasively this can be done. One way of estimating the pressure is by calculating the volume and the time-varying elastance. And with the elastance, using the different equations, they use double Hill equation here to estimate this. So the aim basically was 3 aims: to develop and validate a model-based framework for this non-invasive assessment, to optimize this double Hill equation parameters, and once they validated that model, then as a proof of concept, apply to a few healthy and controls and patients. So the experimental protocol was 12 pigs, 5 on the training set that they underwent invasive measurement of the PV. And then there was a seven pigs that validation, there were the validation set, some of them healthy, some not healthy. So these 7 validation animals, they had their CMR, and they underwent also a catheterization using the PV conductance catheter for assessment. There was also non-invasive assessment of pressure. The CMR was done in a 1.5 Siemens. So once they had the validation, they were going to apply this to the study population, that 13 healthy controls and 28 patients with heart failure. Patients had their blood pressures taken brachially and also underwent CMR. In terms of the data analysis, the pressure data was analyzed using a software, and I'll show you here. So at each heartbeat basically was automatically identified, and the mean pressure curve, it's the pressure curve, and the mean of them was used as a reference. Basically, the highest point is your LV pressure systole and the diastole here. So let's look at the process overview. It's very nicely summarized in this figure. I'm going to minimize this so you could see the whole figure. So basically, the input is the ventricular volume assessed by CMR, and then you have the brachial and the heart rate and the brachial pressure. This is the input, and then the time-varying elastin model, and then is scaled by this input, and it's used to calculate the pressure. So you get the elastance, you put it here, and you get using the volume, you get the pressure, and then you're analyzing this, and you have your PV loops. Going back, the formulas here, sort of the elastance formula, or basically getting your pressure from elastance. So basically the validation, they use different parameters that they had from the experimental model, and then from the in vivo and their model that they had. And I'll show you the correlation. It's basically looking in figure 5, you can see this is the PV model that they had the in vivo in the yellow. It's basically by invasive measurements, and they're on the dashed lines. It's very, very nice correlation, very similar to each other. Also, when you look at the correlation lines in, let me find the results. So you're looking at the model parameters and the in vivo. So you can see there is very good in linear regression. There is very good correlation in stroke work, potential energy, and ventricular efficiency between the in vivo and their own models. So very nice correlation. So this is their validation work. And then now they're going to use this in patients. And so let's go back up. This was again applied to healthy individuals with some patients with heart failure. And the result is summarized. Let me just find the result in just a second. It would be in table. This is the baseline characteristics, basically 13 healthy and 28 heart failure patients. The EF is quite different, obviously 60% in healthy controls and 30% in the heart failure group. The age is different as well. In terms of then table 4, again, the medications, this is what we are looking at basically, and this is the result in the control and patients. You can see, as you can see, the mechanical potential energy was higher in heart failure patients. The ventricular efficiency was lower, and the contractility obviously was significantly lower in these patients. Other parameters, there was no significant changes. So basically, to summarize it, this is a first experimentally validated model to compute the PV loops, and it shows significant agreement with what they had in vivo, and also could support clinical decision making. It could be a surrogate for patients with heart failure. Any questions?
No, thank you very much, Nigari, for presenting that paper, and also nicely circling around the math that is probably very tough to understand. But we have Felicia here, the first author, and I think I also saw Einar Heiberg, the senior author of that paper. And also from my end, congratulations. That's really very nice work. And it really opens a new window for CMR. So first, the question again, did you feel, because obviously, because you have, you use CMR values and then you use the arterial pressure. And we did that years ago, and for many years to calculate end-systolic wall stress, which you can now also derive from the pressure, of course, assuming that the aortic valve is not stenotic, and therefore the peripheral pressure matches that of the ventricle. So, Felicia, do you see any, let's say, any confounders or any sources of probable bias for this methodology? And also, what do you think of the temporal resolution we can achieve with CMR? That would be my question.
Hi, thank you for a very good overview of the paper, Nigari.
Sorry, Felicia, can you speak up a little bit, or I don't know, turn up your volume? So
Is
that's
this better?
Yeah, that's much better. That's
okay,
Felicia Seemann from Sweden.
Yes,
Thanks for calling in again.
So your first question about how...
Yeah, whether you think there are any significant confounders with blood pressure measurements, for example, and others that may affect the accuracy and the reproducibility of the data that we may have missed or so.
Yeah, so I think that we're doing this brachial pressure, we're only doing systolic and diastolic pressure, and we're using a sort of a transfer function to estimate what the pressure would be in the ventricle. And just as you said, it will not work if you have a stenotic aortic valve. And this is also a very rough approximation of this pressure. And I've read a few papers where they're doing applanation tonometry, where they're getting more accurate backward tracking of this pressure. So I think that could be an interesting way of making the method even more robust. The other big limitation is, of course, that, I don't know if you said that, but we did not do any non-invasive estimations of the end diastolic pressure. So this is as an input from the user that they themselves have to estimate this and provide it to the model. But I think maybe this previous paper that we presented could maybe help us in that quest for getting a non-invasive estimation. We did a few sensitivity analysis, so like most parameters are not very sensitive to if you have quite of a big range of this end diastolic pressure. But if you're studying, for example, comparing HFpEF patients to HFrEF patients, you would want to have a good estimation of the end diastolic pressure.
Yeah.
As of the temporal resolution with CMR, which we need to get the whole time volume curve, I agree with the discussion on the previous paper that, of course, we have a better temporal resolution echo, but we have other issues. So I think that we get the best possible volume estimation using CMR. We didn't do any comparisons with any other temporal resolution, so I can't really say if we would get a better pressure volume loop using that.
No, thank you. And in case there are no other questions, Einar was the senior author of the paper and was also overseeing, I think, the overall, or some of the eventual clinical application, or is probably working on that. So what would people, if people would want to use that, what would they need? Maybe a question to both of you, to either do some further research on that or even apply that clinically if that's not too early still.
Shall I answer this, Felicia, maybe, or should we take it? Do you want to?
Sure, go ahead and I'll fill in.
Yeah. So what we would like to see, as you say, now the next step is to do a more clinical use of it, and here we would like to collaborate with other groups. So what we wrote in the article was to have it sort of available for other groups based on collaboration. So if you have the data, then we could supply you with a license key for the module essentially, and then we do it collaboratively. That's sort of the idea we have right now. Yeah. So I hope everybody has heard that. So who's interested in that, and then approach Einar. Certainly, I think, and I will discuss this with my group. I think very interesting because it is using a standard sequence, so it could be using standard images, so it does not necessarily add to the length of the protocol, but it provides a clearly different marker that, of course, increases the number of data points we can derive from a CMR study, and that's the power of CMR, that it's so versatile that you can acquire data on function, morphology, volumes, tissue, but also then if you can get introduced then pressure-related parameters, that's of course a huge additional asset. So that's why I think it's really very interesting. And in addition to that, I don't know how you do, but in our group we have had taking blood pressures clinically for a long time.
Yes.
So it can be used if you have the pressure data retrospectively. So that's
that's a very good point. So you could go back and actually basically do some validation work retrospectively. Although statisticians don't like retrospective designs, I think the number of data points you can get if you use studies that were in the past designed for looking at function certainly would qualify for a retrospective analysis. That's a great point. Yeah.
And even if you have sort of past studies retrospectively, you can now, some years later, look at the outcome and compare how's the PV loop changed, etc. So I think these kind of things. Yeah.
No, that's great. And the tool is that a tool that runs on Windows machines, or what do you need for that?
So you need to download Segment, which is the image analysis software that we develop at our group, and it's freely available for research purposes. But then if you want to use the specific PV loop module, we're asking everyone to just get in contact with us and see what kind of collaboration we can do. So we'll provide a specific license key for that.
Yeah. Okay. No, that sounds great. So I also hope that everybody has heard that. Okay. Thank you very much. And we're already at the top of the hour. Nigar, if you could just unshare your screen, I will just want to, just before we close, point to the next journal club that will happen in 2 weeks from now. And it will be a topic on, it will be, let's say, a very cutting edge one on texture analysis of MR T1 mapping. And then, oh, sorry, I have to work. So the other one will be from Reza Nezafat's group, who's also on the call. Thanks, Reza, for wanting to present these papers, or have these papers presented. Also on T1 mapping, and this time it's on this paper will be on the automatic analysis of cardiac MR images, or cardiac MR T1 maps with convolutional neural networks. So it's going into the machine learning. So I expect a very interesting journal club as well in about 2 weeks. So hope to see you soon, to see you then. And otherwise, thanks a lot for joining, and I hope you enjoyed. Thanks, Nigar, for presenting, and thanks, Felicia and Einar, for the interesting discussion. Take care, everybody, and have a good day or a good evening, wherever you are. Bye-bye.